Hi, welcome back to my channel. This video contains part 1 of Working Stress Design Principle. I will be discussing flexural behavior of beams with solved problems and its solution.
Working stress design principle, flexural behavior of beams. So this would be part 1 of WSD principle. So before we start before we begin the discussion, I just want to remind you that as of May 28, 2020, there's a new list of the allowed calculators for civil engineering, and there are many types. There are Casio, there are Canon, Sharp, and then other calculators that you could use or familiar yourself with. So in the board exam, you will not really adjust so much. So a good tip is that you have to be friends with your calculator. And what I've seen is that the most recommended could be this calculator, which is your F789 SGA, which is a Canon type of your calculator. So it's up to you to decide when to buy or when to be familiar with your calculator. But again, this is a tip that I think would be very, very helpful for civil engineers like you. For flexural behavior of beams, we have first to discuss the concept of bending and stages of loading. As mentioned in our previous discussions, cracking is a very important factor or failure for concrete. And so we initialize the understanding of a cracked and an uncracked section for concrete. So we will differentiate how they are analyzed and how they behave in terms of manifestation of stresses in concrete and in steel. For uncracked stage, this means that the actual moment is less than the cracking moment. In mathematical representation, it would look like this one. Your M sub A is less than your MCR. Again, MCR would be termed as your cracking moment. M sub A would be your actual moment. M sub A is actually also your maximum moment in member due to your service loads. So what's your service loads? It could be a combination of your dead load and of your live load. Your dead load could be your self-weight and your superimposed loads. Your mechanical ducts, your tiles, your floor systems, everything that could be included on dead load and live load. Actual stress is less than the modulus of rupture. So what does it mean? This means that under uncracked stage, your F sub T is less than your F sub R. Again, F sub T is your actual stress and intention, and then your F sub R would be your modulus of rupture. F sub T could also be denoted, as mentioned a while ago, as the extreme fiber stress in your tension or intention. This is FIBER, not victory, all right? So this is a typographical error. I apologize for that. Small loading does not produce tensile cracking. At this stage, concrete resists both tension and compression linearly, elastically with minimal tension in steel. In an uncracked stage, stresses are as follows. Number 1, your concrete stress in compression. Number 2, your concrete stress in tension. And number 3, your steel stress. Again, if it's an uncracked stage, there should be 3 stresses that we will compute or look for, which are your FCC, FCT, and FS. FCC is your concrete stress in compression. We change C to T, it becomes concrete stress in tension, and of course, your FS is your steel stress. The steel stress is the stresses on your reinforcement, and then this one are your stresses at the top or bottom part of your concrete, below and above your neutral axis. To better illustrate, let us use a typical beam which has a total height of h or total depth h and then a base capital B. The reinforcements are assumed to have an area or total area equal to A sub S. If we induce a moment on this manner, wherein this region would be your tension and then this region would be your compression. How do we know that? If the direction of the moment is going away, it's tension. If it's going in, it is compression. When we draw our neutral axis like this, we can assume that our neutral axis could be located x distance from the top of my beam. When that happens, we can now get your transformed section. This transformed section is the building or the basic that we could use in order for us to compute our three stresses, FCT, FCC, and Fs. So how do we convert the transformed section of an uncracked stage? If you can see, this beam is now transformed into this type. The only difference that we could see is your area S or AS, the area of your steel, is now converted to N minus 1 multiplied by AS. Your N is your modular ratio, which is the ratio of your steel modulus of elasticity ES over your EC, minus 1 multiplied by the totality area of your reinforcement. So this is the manifestation or the importance of converting your area of steel to similar that should be similar to concrete, and we can do that by multiplying AS to N minus 1 for an uncracked stage. When this happens, we can now illustrate the stress diagram or the stress propagation on your uncracked stages. This one is where your compression would be. This one is your tension, and this one also is in tension. How did we know? If we look on the direction of our diagram, this is going to your concrete. And because this portion has only concrete, so we will call it as compression in concrete. Going here, this is your steel. Your steel has a direction of the stresses going away. So definitely if this shape or this region is steel, so we will be having, we will denote that this is tension on steel. Consequently, since this one is still going away, but this region is concrete, we would be calling that as tension in concrete. So this is the result of applying the positive moment that's been taken on this original beam. So this three would be our unknowns a while ago. So these forces would now denote or would now produce stresses on this particular regions or locations. Continuing, from the given transformed section, we already know that this is H, this is B, this is your reinforcement, and then this is your X distance from top fiber to your neutral axis. Again, we convert our area because this is the transformed section by multiplying AS to N minus 1. This is my effective depth. The effective depth is from the extreme fiber up to the centroid of my reinforcement. Taking the moment at the top of the fiber, we would have this equation. So how did we get, or how did we arrive with this equation? If you can see, this one is the transformed section of my concrete. This has an area which is equal to BH, which is the concrete area, and N minus 1 multiplied by AS, which is the transformed area of my steel. When I combine the two, that would be my area total. Area total multiplied by my X, because I'm looking for this distance. I will now relate that to the summation of the individual area multiplied by their individual centroids. So in here, this is area total, the global centroid, This is the individual area of my concrete and its local centroid, area of my steel and its local centroid. We are taking the moment at the top of the fiber. So taking a look again, if this region is my base by H, half of that would be its lever arm. That's why H over 2. Also, if this is my area, if we are measuring from the centroid up to the top, the distance would be small letter D, which we call your effective depth. On an uncracked stage, what we look for is the value of X. Upon knowing the value of X, we can now compute for the value of I and A. What's I and A? I and A is the inertia at the neutral axis, which is equal to base multiplied by height cubed over 12 plus BH multiplied by X minus H over 2 quantity squared plus N minus 1 multiplied by AS multiplied by D minus X quantity squared. So what is this equation? This is the total inertia of my transformed section. But because the local centroids of each material, which is concrete and steel, does not intersect or does not lie on the same region as your global centroid, we have to transfer those inertia. And as we know, if we can remember, the transfer is IG plus AD squared. For concrete, let's see. For concrete, we have BH cubed over 12. Base multiplied by height cubed over 12. The distance would be X minus H over 2 quantity squared multiplied by its area. Also, for my steel, yung aking BH over 12, hindi na inilalagay. Why? Because this is a differential strip. So, pagka masyado siyang manipis, hindi na siya nagmamatter. And kahit BH cube over 12 natin siya, hindi na rin siya masyadong magiging parang addition to this one. So, we will just eliminate, parang hindi man eliminate, we will not consider it anymore or disregard those value. We will go straight to AD squared. So, this is the area, as we can see from the figure, multiplied by the distance D minus X quantity squared. So, what's my D minus X? That's the distance from the neutral axis to the centroid of my bars. What's X minus H over 2? That's the difference between the centroid of my concrete, which is here, and then X, which is the centroid of my transformed section. Upon knowing these values, we can now compute and proceed with the computation of the stresses. Number 1, concrete stress in compression is equal to mx over I and A. How do we know that? Because your FCC is actually the bending stress caused by compression in your concrete. And in order for you to compute for that, you have to use this formula. M multiplied by X over I and A. Next, concrete stress in tension. It's FCT equal to M multiplied by H minus X over I and A. For your steel stress, F sub S is equal to N multiplied by M multiplied by D minus X over I N sub A or I and A. So now, let's analyze the values. Why do we use X? Why do we use H minus X? And why do we use D minus X? So for FCC equal to M multiplied by X over I and A, if we'll take a look on the figure, the transformed section on this region is experiencing stress in compression. And the extreme fiber distance for this region in which compression is manifesting is equal to X. Going over with this region, which is also concrete, that would now be the extreme fiber distance. But since we know that from tip to tip, that's equal to H, when we subtract this value, we can now compute for the value of this depth, which is equal to H minus X. And so, that would be the stress caused in tension or stress in concrete caused by your tensile force. Lastly, because we are now taking the steel stress on my steel, So from the neutral axis, I should compute for the extreme distance or fiber distance, which would be equal to, if this whole region is t, subtracting x would be this value, d minus x. If this does not make sense, on the next slides, there will be a sample computation and illustrations on how we can use these equations. Now that we know the uncracked stage formula for concrete stress in compression, concrete stress in tension, and steel stresses, we'll now proceed in discussing your cracked section. This is my cracked stage. The cracked stage is the opposite of your uncracked stage, wherein the actual moment is now greater than your cracking moment. Here is your mathematical expression. M sub A is greater than MCR. Actual stress is greater than the modulus of rupture. How do we represent that in a mathematical equation? F sub T is greater than F sub R. Working strength design using service loads. Service loads are actual and factored loads that produces tension cracks in concrete. Therefore, concrete resists compression only and steel resists all tension under linear elastic stage. So unlike your uncracked section in here, basag yung kanyang nababasag yung kanyang bato. So pag nababasag yung bato, imbis na maging tatlo yung hinahanap nating stresses, dati kasi kanina yung uncracked section, meron kang stress sa compression sa concrete, stress sa tension sa concrete, tapos ay stress sa steel. Ito ngayon, dahil basag yung kanyang bato, wala yung ibabang concrete. So meron ka lang top na concrete, tapos meron kang steel sa baba. And when that happens, these are your unknowns. The concrete stress, FC, and then your steel stress, which is F sub S. So the main difference between your uncracked and cracked stage is that for uncracked section, there will be three manifestation of stresses. Stresses on your concrete due to compression and due to tension, tapos ay stresses on your steel. Ito naman, dalawa lang pag cracked stage, concrete stress and tensile stress. So how do we illustrate the manifestation of these stresses? So again, we consider a typical beam. The beam is height h, with base B, and with area S. If we induce a moment which is nominal from the service loads that we took into considerations, again, service loads are combinations of your dead load and live load, and dead load is either a combination of your superimposed load and your self-weight. Drawing your neutral axis, assuming that this would be the center of gravity for this section or for this figure, we could now see, or we could now construct the transformed section. The transformed section would now look like this. So unlike before, buo yung concrete mo. Kasi nga uncracked siya eh. Buo yung concrete tapos may steel. Ngayon dahil cracked section siya or cracked stage siya, natitira na lang yung concrete dun sa distance nung x ko. Kung ano yung x value, yun yung depth nung concrete ko. Nasasalo lahat nung stresses mamaya. Tapos itong stage na to, ito naman yung aking steel. Yung steel ko na-convert siya. Kanina n-1 multiplied by as. Pero ngayon, pag crack stage, n multiplied by as. So how do we now analyze the stresses that are manifested on your material, yung mga natirang material? Dito, yung aking concrete under compression. Hindi ko na kailangan ilagay kung because of compression or because of tension. Basta meron siyang force in terms of compression. Tapos ito, going away, that is my steel. Paano ko nalalaman? Kasi sa direction nung aking moment. Yung moment ko papunta dito. So kung nasan yung arrow, dahil pushing yon, compression siya. Ito, palabas yung aking tension. Pag ganyan, ibig sabihin, palabas yung force ko. Paano pag binaligtad ko, nilagay ko dito yung aking moment? Ibig sabihin, baliktad yung bakal ko. Ilalagay ko yung bakal dun sa kung nasaan yung tension force o kung nasaan nagsisimula yung moment. Bakit? Kasi nga, di ba napag-aralan natin na yung concrete, mahina siya sa tension. So, dapat ma-reinforce siya against tension ng reinforcements. So this is caused by this nominal moment. How would be the transform section look like? So from the original figure, it would look like this one na. Measuring your values, this is your neutral axis, this is the depth of your concrete block, and then this is the effective depth of your reinforcement. This area is now converted to n multiplied by a sub s. Taking the moment at the neutral axis, so for crack stage, instead of taking the moment on the top fiber, dito na lang sa gitna para simple. Meron akong iikot na concrete, meron akong iikot na bakal. This would be equal to b multiplied by x over 2 equal to n multiplied by as multiplied by d minus x. So what is this? B sub x or bx is my area of concrete. The area of my concrete has a centroid equal to x over 2, which would be the lever arm of the figure. Ito naman, n multiplied by as or nas would be the area of my steel, and then the lever arm from this centroid up to the neutral axis would be equal to d minus x. We can now compute for x. Para saan yung x? We are computing that because we want to compute for my inertia at neutral axis. So this one is the simplified form. The simplified form from Ig AD squared of the concrete plus Ig AD squared of your steel would be bx cubed over 3 plus n multiplied by as multiplied by d minus x quantity squared. So ito, i-explain ko sa problem din mamaya. Bakit siya naging ganito na? Para sa uluhin mo na lang or i-memorize mo na lang na INA would be equal to bx cubed over 3 plus NAS multiplied by d minus x quantity squared. In case ayaw mo mag-memorize, tandaan mo lang kung ano yung manifestation of uncracked stage at ng crack stage. Basta tandaan mo ulit na kapag uncracked stage, 3 stresses, crack stage, 2 lang. Your 2 stresses now would follow that it can be computed as concrete on steel is m multiplied by x over INA, pareho siya sa FCT, or FCC, sorry. And then, wala na akong FCT, pero meron akong FS. Again, n multiplied by m multiplied by d minus x over INA. So, ito, pareho sa FCC, ito, pareho dun sa FS. Yung FCT ko lang yung nawala. Bakit? Kasi nga, basag na yung concrete sa baba. Hindi na sinasalo kahit ano pa dun sa forces. Inassume natin na crack section, na nag-manifest na cracked section siya. Now, before we test our understanding of cracked and uncracked stage in a problem-solving way, let's first recall some values for the concept of bending and stages of loading. So number 1, your modular ratio N is equal to ES over EC. For normal weight concrete, your EC would be equal to 4700, the square root of FC prime. EC is equal to 200,000 megapascals. It is always rounded to the nearest whole number. So what does it mean? For example, the ratio becomes 9.29. Your N would be assumed to be 9.0. If N is equal to 9.79, your N would now be rounded to 10.0. Again, it is on the nearest whole number. This is based from the NSCP. Flexural stress FB is equal to FB equal to MC over INA. This is your flexural stress or bending stress. Tandaan lang natin na baka nagagamitin natin to dun sa mga stresses on your concrete, your steel, and others. Modulus of rupture or F sub R is equal to, related to the bending stress, MCR multiplied by CT over IG. From the code, my modulus of rupture is 0.62 multiplied by the square root of FC prime. This one is for normal weight concrete kasi may lambda pa dapat dito. Either 1.0 yon or 0.75. Dito din, pwede siyang maging different kapag yung aking weight of concrete is not normal weight or not 24,600. Effective depth is measured to be your total height multiplied by your concrete cover multiplied by your stirrups diameter multiplied by the diameter of your bars over 2. So ito, mamaya may explain natin kung bakit naging ganyan siya. Basta ang tandaan mo lang yung H, total height, yung D, effective depth. Tapos, inuurong lang natin siya. From the total height, bawasan natin tong mga unnecessary distances para malocate ko yung height ng effective depth. Pero some problems, binibigay mismo yung effective depth. So, hindi na natin kailangan mag-solve pa. Pag wala nun, ito yung formula. Concrete cover is CC. That's here. Usually, it's given for your beam 40, for your columns 40 also, for your foundation 75. In case you're unsure, you have to check on section 420.6.1.3. And with that, I think we're ready to solve problem number 1. So your problem number 1 is divided into 2. Determine the properties of the transformed section and calculate the elastic stresses of a given beam if letter A, your moment given is 30 kilonewton meters. Your letter B, what if the moment is 70 kilonewton meter? And we use your ultimate strength of or compressive strength of your concrete FC prime equal to 21 megapascal. This is your beam. Your beam has been given the dimensions total height equal to 500, base equal to 300, and then effective depth equal to 425. There's no need for us to use the formula shown a while ago kasi pinigay naman na niya. Tapos, it's now reinforced with 3 32mm diameter bars. So how do we solve letter A, letter B for this type of problem? I will give you the solution. Number 1, for letter A, we must first compute the cracking moment. After computing the cracking moment, we can determine whether it's cracked or uncracked. Determining crack or uncracked section would now enable us to compute for X and INA. This is where we locate the neutral axis of your section. Number 4, we can now resolve whether if it's uncracked, tatlo, FCC, FCT, FS. Kapag ka-crack section, dalawa lang, FC and then FS. For letter B of number 1, ganun lang din siya. First, we compute for the cracking moment. Letter B, we determine, or number 2, we determine if crack and uncracked section. Upon knowing the stage of cracking, we can now check for the location of your neutral axis and then compute for INA. Again, this is the inertia at your neutral axis. Then we can resolve whether it's uncracked or cracked. These are the following values to be considered. For letter A, we're given the moment is equal to 30 kilonewton meter, and then my FC prime is equal to 21. Compute the cracking moment. So how can we compute for the cracking moment? We go back to the following, to the available formula that we can remember. So before this problem, we recall that your modulus of rupture, F sub R, is equal to MCR multiplied by CT over IG. Also, your modulus of rupture can be computed as MC over I. To compute the cracking moment, we need to isolate B by H section, 300 by 500 millimeters. For the given, your C sub T is equal to 500 over 2, and your IG would be equal to BH cubed over 12. So what does it mean? Pagka step 1 tayo, tanggalin mo muna yung bakal. Pag tinanggal mo yung bakal, i-analyze lang natin siya ng concrete lang. Bakit? Kasi nga cracking moment. Cracking moment of your concrete. Now, your resulting figure would be a 300 by 500 millimeter concrete. That would have the height of 500 and the extreme fiber distance, because it is symmetric, is 500 over 2. So, nakalagay na siya dito. Tapos, dahil rectangular siya, IG would be equal to BH cubed over 12. So, from the formula that was mentioned a while ago, this is the possible equations to use. From the bending stress of modulus of rupture, FR is equal to MCR, CT over IG, and your FR from your NSCP is equal to 0.62, the square root of FC prime. Ito dapat may lambda, pero dahil hindi naman niya in-specify, we will assume right away that we are using 1.0 for the factor. Continuing, MCT multiplied by CT over IG would be equated to 0.62 the square root of FC prime. Bakit? Kasi dito nga dalawang to, yung yung F sub R, dalawa yung possible values niya. So, i-relate natin siya para makuha natin yung cracking moment. Paano natin makukuha? CT now is given to be 500 over 2. IG is already given to be BH cube over 12. And 0.62 is a constant. The square root of FC prime would be 21 megapascal. So giving or inputting all the values, we could now have this working equation. MCR is the only unknown. Therefore, we can compute that MCR is equal to 35.515 kilonewton meter. Let's store that on our calculators at letter A. You can store on different letters, but for this lecture, I want you to store the value in your calculators, particularly on letter A. We're done with step number 1. Step number 2 would be to compute for the cracked, or to determine, whether it's a cracked or an uncracked section. How do we do that? Simple. We just have to relate your MCR to your M. Comparing the cracking moment to the actual moment, it turns out that M sub A is less than MCR. Bakit? 30 is less than 35.515. Pag ganon, ibig sabihin, this one would be an uncracked section. Why is this important? This is important for step number 3. Step number 3 is knowing whether, or step number 3 is looking for your neutral axis. We compute for X and INA. It is important to know whether it's cracked or uncracked section because we can now illustrate your transform section. The transform section for an uncracked stage would be like this. This is where we take the moment later. This is the location of my neutral axis, assuming that this X is measured from the top fiber. It's labeled to be 500, 300, and the conversion of my area is automatic to be N minus 1 multiplied by AS. Effective depth has been given, which is equal to 425. Computing for the values, we have first to compute for your modular ratio. The modular ratio is equal to ES over EC. Again, it's not mentioned what concrete we use. Therefore, we will assume it is in normal weight. The normal weight, therefore, would for the normal weight concrete, the modulus of elasticity would be 4700, the square root of FC prime. The modular ratio would now be equal to 9.29. But since your modular ratio should be rounded to the nearest whole number, we will use N equal to 9. Next, we compute for the area. In here, there are 3 32 millimeter diameter bars from the figure before. That's why we have to multiply it by 3, the singular area of my concrete, which is pi over 4 diameter squared multiplied by 3 is equal to 768 pi millimeter squared. It is important because when we take the moment at the top fiber, we can have this equation. B multiplied by H plus N minus 1 multiplied by AS multiplied by X equal to BH multiplied by H over 2 plus N minus 1 multiplied by AS multiplied by D. This 1, BH plus N minus 1 AS is my area total. Area total multiplied by the global X distance is equal to the summation of your individual areas multiplied by their individual distance to top fiber or local distances. So ito, area of my concrete, BH, its distance is H over 2, again from the top fiber. N minus S multiplied by AS, or N minus 1 multiplied by AS, lever arm would be D. In here, we are computing for X. So we will insert all values now from this figure. We can now compute for X. X would turn out to be 269.951 millimeters. We store that on B of our calculators, or we store that on your calculators. You must check if this value is correct. So you can use shift solved, or you can simplify the equations first. or the equation first and then compute for your x. So before we proceed, let us first examine this equation. So at x is equal to 269.951, we can see that this is the location of my global centroid. Knowing the global centroid, we can locate for the local centroid of my figure, which is here. Ito yung ating local centroid ng concrete ko. It's important. Why? Because when we're looking forward or when we're looking for the computation of I sub n, I and A, we are to have your summation of your transfer of inertia. Kailangan yung mga figure ko, makuha ko yung I and A, which is the inertia at neutral axis. But because there is distances between your global to local of your concrete and of your steel, I have to transfer them. This is now the expanded equation for I and A. Bakit naging ganito siya? Let's first label, this is concrete, this is steel. Okay? So, let's first go back on the label. First, we focus on the equation. This first two values would be designated for my concrete. How does it relate to my figure? In here, if we take a look, we're looking for this distance. As we can see, BH cube over 12 is IG, or the gross inertia of my concrete, plus area multiplied by their distance. This point up to this point is equal to H over 2. However, we already computed that this value would be equal to X. The difference between the two is X minus H over 2 quantity squared. Next is this figure. Again, because this is a strip and it's very, very little, or it's negligible, so we will just not consider that. We will assume that IG for steel is 0. Therefore, continuing, n minus 1 is the area multiplied by AS, or n minus 1 AS would be the area of my steel multiplied by the distance squared. Paano siya naging d minus x? If we take a look again on this figure, we can see that this one is from this point up to this point is d, effective depth. From this point up to this point is x. Therefore, the difference between the two is d minus x, in which we can put now your x value, which is 269.951. Remember that you have to use the exact values. Inputting those values would result to this equation, and therefore, my INA, or inertia at neutral axis, would be 3648.729 times 10 to the 6 millimeters to the 4th. And let's store that on C of our calculator. Now that we know those values, we can now compute for FCC, FCT, and FS. Bakit? Because this is an uncracked section. For an uncracked section, there is compressive stress due to compression, and there is stress in concrete due to compression, there is stress in concrete due to tension, and there is stress in your steel. So ito yung ating figure kanina, nilagyan lang natin ng mga values. This is 269.952. But again, we need to use exact values stored on letter B of your calculators if you followed the step-by-step procedure a while ago. Compression stress in compression would be given as this equation. Your M would be equal to 30 kilonewton meter. Your X is 269.952 and INA has been computed already. The correction factor is equal to 1000 squared. Putting these values on your calculator, we can now compute that FCC is equal to 2.22 megapascal. I need you to try to compute for these values, and why you should be multiplying it by 1000 squared is because this is in millimeters, this is in millimeters. We need to conserve your units. This is in meter, so we need to correct that, multiplied by 1000. This is kilonewton, we need to correct that, Therefore, it is again multiplied in 1000. The resulting value would be equal to Newton per millimeter squared. And Newton per millimeter squared is megapascals. Next value would be concrete stress in tension. FCT is equal to M multiplied by H minus X over INA. Putting the values, this is my new equation. Again, the correction factor would be 1000 squared. This is not 1000 times 2. This should be 1000 to the second power. Putting these values and computing for FCT, we would result to 1.89 megapascal. The last equation would be the stress or the steel stress equal to Fs. Fs is N multiplied by the moment multiplied by D minus X over INA. And putting the values, we could now look for, or we could now solve for Fs. Fs is 11.47 megapascal. So these are the stresses yielded on your concrete when it is subjected to a moment of 30 kilonewton meter. Note, use exact values when computing stresses, round off only, and the final answer. To better understand again our knowledge of